This is actually a little bit more than IOLoop delay. We'll be covering a little bit of any event and the promises module as well. So I have to apologize to Glenn. This afternoon I went and looked at the outline for his talk that he gave at MojoConf last year, because I'd forgotten that what your topic was, and it turns out that a lot of what I've done here for MojoConf. It was online, so I looked at the outline. So there's a lot of overlap. If you went to MojoConf in Sweden or Norway,
Yeah, if anybody was in Norway.
there'll be some overlap, but it's not intentional.
There was, I think, 50 people. Okay, great.
Okay, so here's our plan for the evening. We're going to talk about the difference between blocking and non-blocking code. We're going to talk about microservices. We're going to talk about how cool event loops are and how bad most event-driven code is. And then we're going to look at some options to overcome some of the problems with event-driven code. All right. So before we get started, I know we've just had sandwiches, but it's now time for breakfast. All right. We're going to order pancakes, and we're going to order a soft-boiled egg and some orange juice. We go to our favorite restaurant, and the chef in charge is Blocking Chef. So Blocking Chef, he knows how to do everything. He's very qualified. The first thing he does is mix the pancake batter, and then he heats up the skillet because you can't cook pancakes on a cold skillet. The next thing he does is cook the pancakes. Everything's done in the right order for Blocking Chef. Now we get to boil some water, right, because we need to cook our eggs. Once the eggs have been cooked, we can cut the oranges and then juice them. So you see the problem here? All right, this is going to take way too long. We're looking at a 15-minute breakfast here, and that's going to kill us. So, you know what, and the pancakes are going to be cold, and the eggs are cooling already. So, you know, what happens to Blocking Chef? He's out of there, right? He gets fired. So then we get non-Blocking Chef. He's better looking and much smarter than Blocking Chef. He knows that he can do a few things at the same time. He's got timers set up in the kitchen, and he knows that he doesn't have to wait at the skillet for it to heat up or at the water for it to boil. He can do all these things at the same time. He gets to cook the pancakes. He gets to cook the eggs. They don't take his attention. And he, like I said, he's got alarms and things that will help him know when something is ready to do. Let's see. So we're down to 6 minutes now for breakfast. That's awesome. Blocking Chef gets a big twinkle. He's awesome. Non-Blocking Chef, sorry. So before I move on, I want to show you some numbers. These numbers are a little bit old. Jeff Dean is an engineer at Google, and he gave a talk 5 or 6 years ago about, he called it numbers everyone should know. And these numbers are a little bit out of date, but the scale is still pretty accurate. There's no SSDs in here. Those would be, you know, closer to the memory numbers. But you can see a level 1 cache reference is half of a nanosecond. A nanosecond is a millionth of a second. We've got milliseconds, that is 1,000, micro times 1,000, nano times 1,000 again. Branch mispredicts, et cetera. You can see this. Now when we get into the green numbers there, you can see how much it's orders of magnitude slower than anything else. Now we're still, disk-seek, that's 10 milliseconds. That's still, you know, for a human, that's really fast. But in computer time, that's an eternity. Your computer is sitting there wasting cycles. It stops, and it's got to go wait and get all the data back, and then it can go on again. So if it has to block and wait for input-output, you're not getting your money's worth out of your CPU. You could just be doing so many other things with those clock cycles. So who here has used Modulicious before? Okay. We're going to do a quick review of Modulicious Lite because a lot of the examples today are obviously about Modulicious. So this right here is an entire Modulicious program. If I were Perl, the first thing I do is I notice that we set up what's called a route. This means that our Modulicious application is going to listen for HTTP GET requests on the /foo URL. So if anyone opened up curl and typed in http:// you know, some host name /foo, this is what would respond. We set up a there's a subroutine handler there. It's called a callback. That when that runs, when that URL is hit, that callback will run. The next thing we do is start our application. This starts the Modulicious daemon and gets the event loop going. Once that URL is hit, we go into that controller now. The C stands for controller, as in the model view controller pattern. The next thing we do is we invoke render, and then finally we set the content type to application JSON and serialize that hash reference. So we'd get a little JSON document that consists of foo::bar. So it's very concise, very powerful patterns, Modulicious Lite. A few other fancy things Modulicious Lite can do. You can do a get from the command line to test your application. That top one, my app get/foo, will actually launch your application, start the event loop, make a get request, get the response, and then shut down your application again. Very handy for quick testing of things. The next one is how to start a daemon. This is it does not background itself. You would have to Control-C out of this, but it's nice if you want to open something in a terminal and then hit it with your browser or whatever. Hypnotoad would be like a production. It does a pre-forking daemons like Apache does. You can list the routes that your application currently supports. You can run some tests. It's pretty powerful. So that's all we're going to talk about Modulicious Lite tonight. Let's move into microservice architectures. So microservices are small HTTP or other TCP services. They follow the Unix philosophy of do one thing, do it well. Small is beautiful. Composition. Composition is a functional programming term. In Unix, you might think of composition like when you do a grep on a file, and then you pipe it to awk, and then you pipe it to sed, and then you do some more things. That pipeline is a form of composition. And then text is the universal interface. That's a Unix tenet. And in microservices, it's usually JSON. It doesn't have to be. It could be XML or even HTML. But the idea is that we speak HTTP everywhere. So even web servers would also have built into them a small web client so that the client can go out and talk to other web servers if it needs to. And Modulicious is really designed for this kind of architecture. So tonight, what we're going to build is a little microservice. It will do the following things. It will go get our source IP address. Now, if you're behind a NAT like we are tonight, getting your source IP isn't always easy. You have to actually go out of your NAT and ask, what is my IP? What do you see me as? So we'll do that. Once we get our IP address, we can get our geolocation. That's your latitude, longitude, some other things like that. That's based on, it's not really accurate. It's just based on your carrier. If it's Comcast, it'll be within the city probably. And then using the geolocation, we will be able to get the weather, the current moon phase, and the air quality index. Technically, the moon phase is not based on your latitude, longitude. It's based on the time of day, but we're going to pretend it's based on your latitude, longitude. What?
You sure? I can't get past that.
I'm dang sure, man.
Okay.
Give it an epoch time and it's done. Okay, so, yes, if anyone has any questions, please interrupt. I'm okay with that. So I wrote a few little microservices for our demo tonight. If you want to hit those right now with your laptops using curl, you're welcome to. So my IP is a little service that you hit it with curl, and it comes back with a little JSON that tells you your IP address. Very simple. Doesn't do a lot. So that's the IP of demo. Demo is in my hosts file. I use demo. Hey, Jace. I use demo because I didn't want ugly IP addresses all over the place. The next microservice is a geolocation. This is a third-party thing. I did not write this, but it's very handy. You pass it an IP address, and it will come back with your latitude, longitude, and lots of other cool information. Your carrier, Comcast or whoever, Google Fiber, if you're lucky in Provo. Don't know anyone like that. I wrote this one. This is a little moon phase POM named after the old BSD program, a phase of moon. And you just hit that. It will, based on the current time. You can also pass it a time. I didn't illustrate that here, but and it will tell you the current moon phase. Very handy. And then another microservice that is weather. I wrapped the forecast IO. If any of you need to ever do like weather, forecast IO is amazing and it's free. They give you 1,000 requests per day, but it gives you a truckload of JSON information. Very cool stuff. It gives you the forecast for the next 5 days. I mean, it's amazing. You could do great command line weather apps, and people have, with forecast.io. I did this partly to shrink the URL and partly to hide my access key. But if you hit this URL right now, you'll still be using my access key, but you still won't know what it is. Air quality index. I started writing a little scraper for weather.gov and gave up because they used classes instead of IDs for everything. So it's nearly impossible to scrape cleanly. And frankly, I just wasn't worth it. So what I wrote was something that returned a little JSON document. It's the same document every time. Small particulate matter, index 22. That's actually good air quality, by the way. Microservice slow. I wrote this one mostly to illustrate the effects, exaggerate the effects of latency. So a 2-second, most of these microservices respond very fast, but when you hit a slow microservice, it can kill your app. So that's the number of seconds at the end there you want it to wait. Give it 10, it will wait 10 seconds and then give you a reply. Okay, so this is a first stab at it. We're not going to hit all of the microservices in this first example, mostly for space reasons. But here's our Mojo app. The first thing we're going to do is make a call to, so UA is the user agent. It's like a browser embedded in Modulicious. It's very cool. We're going to do a GET request on that URL. That will block. And when that response, so HTTP consists of requests and responses. So we're making the request, and that TX1 right there will not be assigned until the response comes back. So this blocks. Our code just goes and stops until the request comes back. Then it can proceed. And then we assign the phase of moon. That TX1, res stands for response. There's a JSON parser built into Modulicious, so it can parse out the response of the request that you made. And we're going to assign that to the POM variable, phase of moon. The next we call slow, just to see the effect of maybe adding a slow microservice in there. When that's done, we will go get our IP. When that's done, we will finally render back to the client a little JSON document that consists of phase of moon, how long we waited, and the IP address. So how does this perform? It would perform as you would expect. We get about 0.4 requests per second. That's horrible. You'll notice that I used work, WRK, as my benchmarker. It's like Apache Bench, but it's a lot more modern. It can do threads and a lot of nice things. If I change those numbers, C is connection, T is threads. If I bump those up, and D is how long it will try and hit it, 10 seconds. If I bump those up, I wouldn't get any requests at all because they would just all be outstanding. So I mean, it just bumps the average way down. So this is what we get. It's really bad. So anyway, so what do we do when we're faced with a really slow? If our server is really slow and people are blocking, right? So if somebody makes a request, it's going to take 2 seconds, at least 2 seconds, for them to get the response back. If someone else is waiting in line, they're going to have to wait till that request is done before they can get theirs handled. And that's why blocking is so bad. So what do we do? We could use Hypnotoad. What Hypnotoad does, like Apache, it does a pre-fork. It will fork off as many servers as you tell it. And so now we can handle 100, 1,000 simultaneous requests. So it feels a lot more responsive. We could handle 1,000 clients hitting our site at the same time. The problem with that is that if we're not getting 1,000 clients right now, we've got 1,000 servers sitting out there chewing up all kinds of CPU, polling, waiting for something to happen. It's really a terrible use of CPU. And it really doesn't, it still does not scale well. So you've got your one daemon, it's handling the one request, but it's doing nothing the entire 2.5 seconds that it could have been handling other requests. So blocking is just a terrible thing. So now we need to kind of change our mindset into what does non-blocking look like? Here's one example. If any of you have ever written a signal handler in Perl, it looks something like this. You assign to the sig hash, which is a global built-in variable into Perl, that when we get the int signal, we want this code to run. And then you could do a while one. You could copy and paste this program into your terminal right now, and then it will sleep forever. And then as soon as you hit Control-C, the operating system gets that signal, and it says, oh, hey, somebody wanted to know about that signal. It was that program guy I met. So it says, here's the signal, and then it runs the subroutine that we gave it. Very cool. Here's another example of asynchronicity that you might be familiar with if you've written some JavaScript. If you've used jQuery, you have certainly written some code with callbacks. Built into the browser is an event loop, and it runs all the time. And what it does is it's sitting there listening for mouse movement, keystrokes, DOM events, network events, all kinds of stuff. And while nothing's happening, it's just waiting. But sometimes something will happen. So in this case, what we wait for is we're waiting for the ready event to fire on the DOM. This tells we've told the browser, hey, when the DOM is ready, run this little function. And so our page loads, the DOM is now ready, that function runs. And this is actually another function we're going to run that's non-blocking. We make an AJAX call out to perl.org. There's a callback inside of a callback. When that response comes back, then we run, we pop up the alert dialog, which actually stops the event loop. Don't use that. It's very nice. So this is a callback and a callback. These are pretty common patterns you see in event loopy kinds of environments. So we're talking about asynchronous things. Tonight, for the purpose of this discussion, we're not going to be talking about parallel programming, where you have multiple cores handling, doing something for your program. We're not going to be talking about threaded programming, where multiple threads might be helping your program. What we're talking about is a single-threaded, event-driven, non-blocking system, for simplicity's sake. Yes, thank you. So what are event loops? They're like mysterious. Here are 5 event loops that I've played with over the years. There's the venerable event loop, and that is how you access it. You load it, and then you say loop, and you don't know what happens after that. There's EV, which is a very high performance based on libev. EV run. You've got PO, good old PO. I remember good old PO. IO async, which is a newer one, very nice. And then at the bottom is Modulicious. Mr. Ryan?
If you remember from my talk, we used IO select as our async event loop.
Yep. OK, so I see this and I go, what the heck is really happening? What's going on? I had no idea what was going on. So what we're going to do is we're going to quickly write our own event loop. OK, this is how event loops work. The first thing we do is we set up an event queue. That's our list up there at events. And then the next thing we do is we register our intent to be notified when something happens. In this case, when a network event happens, we want to run this code. I got some network data. So those are typically called watchers or listeners or handlers. They're given a variety of names. Here's the entire event loop. And this is not going to be a high-performant event loop, but it will work. We say while sleep 1, then we go and we check to see if there were any events. Any events that might have happened, we push them onto our event queue. The next thing we do is we take the first event off, and then we split it up. We've got the event, which would be like network or disk or something like that, and then the data, like here's your web page that you asked for, or whatever it might be. Here's some bytes from this sector on the disk. Then we invoke the watcher that we gave it. It's a subroutine reference embedded in a hash. This is a kind of a nifty little pattern. And then we pass it the data. So in our case, see, we're going to shift off at the very, let me see if I can get my mouse working here. We're going to shift off here what we get, and this is what we're passing into our subroutine right here. Very nice. So what does check events look like? Well, I'm sorry, I'm really just pushing the abstractions further and further down. Check events does a loop of things. It will say, oh, do we have any network events going on, and is anyone listening for event network? Because we don't want to create events for things that no one cares about. We're just going to drop those on the floor. And if so, then we create a new my mouse. We create a new event here. It's a network type event, and there's the data that came back from the network event. It might be a timer event. It might be a signal that the operating system sent or received. It might be some disk activity. There's all kinds of events that the operating system knows how to handle. And if there were no events, then we just simply return an empty list. And this will just go on forever. As long as there are watchers or listeners that want to be notified, the event loop will keep running. So again, event loops are kind of like callbacks or signal handlers. In this case, the operating system is the event loop. And we tell the operating system, hey, run this chunk of code when the int signal happens. OK. So there's up at the top there, again, I keep having to abbreviate it for space reasons, but at the top we have our blocking program where we go out to phase of moon, and when that's done, we go to the slow. Down below is exactly the same code, but running in non-blocking mode. Modulicious user agent, you can make requests in blocking mode, where you wait for the transaction to be assigned, or you can make it in non-blocking mode. So here we have our blocking call, and you can see that we wait for the transaction to come back. In the non-blocking, we just make the call, we fire it off, and we say, hey, when that comes back, run this code. And so the transaction finds its way into the callback, because that callback is going to run when the response comes back. In there we have there's our get the code out of that. We stick that into our callback as well. And because we want the second URL fetch to happen after our first one, we put it in that callback. And then we assign the transaction, and we get the data out of it, and so forth. So in event loops, non-blocking functions don't return anything useful. You shouldn't expect them to, because it hasn't happened yet. That's why you give it a callback, and the useful stuff would go into that callback instead. So how does this one perform? It performs awesome. We were getting 131 requests per second. You can see that I was able to crank up the number of connections to 10,000, 100 threads. That's a 300 times speed up. That's really good. So now, each individual request still takes 2 seconds, because we make the first call, then we make the second call, then you get your response. But the difference is that while we make the first call or the second call, we're not blocking. Those were just events, essentially, we've stuffed into the event loop. And we can accept hundreds or thousands or tens of thousands of connections, just one after the other. And they're all asking for things, and we just queue it all up. And when the responses come back, we shove them back out the door. So very awesome. Non-blocking is the way to go. OK, so what are the drawbacks, right? You're like, why doesn't everybody work like this? Well, there are some problems. Part of the problem you get with non-blocking code generally is it's called continuation passing style. The continuation is that subroutine plus its context, the closure. That just kind of gets stuffed down from call chain to call chain. And it makes it's hard to reason with. It's hard to debug. We don't get event loop concurrency, meaning you can, it's just more difficult. We have to do one thing after the other here. Instead of, what if I wanted to make 5 calls at the same time in my callback? That's a little bit trickier. Excuse me, I'm going to grab a tissue here. And then there's the flow control and error handling. It becomes a nightmare when you've got something way down in a callback that has an error, and you've got to figure out where to catch that and what happens when. It's tricky. So this is a picture of the famous pyramid of death that you get, or also known as callback hell. You make one call, you make another in that one, you make another in that one. It gets deeper and deeper. And Glenn is here tonight, so I include this for your enjoyment. Yeah, you get to non-block while you non-block. It's a lot of fun. All right, so we know that blocking code is horrible. Non-blocking is great, but the problems with non-blocking code is that it's hard to work with. So what are some solutions to that problem? We're going to look at three different ways that very smart people have come up with to deal with this. First, we'll go over any event. What any event gives us is ad hoc flow control. It gives us a set of powerful primitives that allows us to construct really whatever we want. It's low-level event handling stuff, but it's super powerful. Condition variables and a lot of other really nice goodies in there. You could build your own nice event system on top of it, and people have. So this is any event here. This is an any event program. We're going to pretend we're the Perl interpreter again, okay? So here we go. We're going to run our program. Here's our console down there. Fetch URLs. So the first thing we do is we hit that first line of code and we say, make me a condition variable. So a condition variable is a little object that has a couple of properties or attributes. It has a counter and it has a callback. Now once you've created it, it's empty. There's nothing in it. So the next line of code we do is we set that callback. We set it to some subroutine that says all URLs are done. The counter's still 0, but we've got a callback now. Next, we call CV begin. We're calling the begin method on our convar, or condition variable. The only thing that begin does is it increments the counter. That's all it does. That's its only purpose in life, is to increment the counter. So why is that useful? We'll see in just a moment. The next thing we do is we make a non-blocking call to URL 1. What that does is it makes we set up our URL request and we fire it off. It's out the door and on the network, and we're waiting for something to come back, but we don't block. It's in the event loop. We do register our intent. We say, hey, when that comes back, give us, run this subroutine here. Then we hit begin again. That's going to bump the counter up to 2. We make another non-blocking call to URL 2. That one goes out the door. And then we register our callback with that. The next thing we do is we print running. So there that is on our console. And then we enter the event loop. We do ev run. And so it looks like the end of our program because it's at the bottom, right? But ev run, so what does ev run do? Well, it waits. That's all it does, is it waits for things to happen. What are the things that it's waiting for? Well, we've told it. There are 2 network things that we're interested in hearing about. We gave it some callbacks. So in time, we will get the response for URL 2 because it was faster than URL 1. We know what happens. It runs the callback, right? We run the get callback. We say URL 2 is done, and then we run CV end. Now, CV end decrements the counter by 1. So now it's back down to 1. We wait some more. Eventually URL 1 will come back. We'll run that callback. And we decrement the counter again, the convar. Now the convar, when the convar gets down to 0, ding, 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 a little magic happens. What happens is it runs its callback. It fires off its callback. So that is how any event condition variables work. There's some other really nice things about condition variables that we're not going to get into with send and receive and some other nice things. But you can also pass data between convars and accumulate stuff in that callback. But we're not going to get into that. So it's very cool. It's very powerful. You can see that it's a nice flat linear thing. Here's our program. We're going to hit phase of moon. We're going to hit slow, and we're going to hit my IP. You'll notice the first thing we do is we set up a hash of responses up there at the very top, right there. The next thing we do is we make our convar, our condition variable, and give it a callback. We invoke a bunch of begins. We're going to fire off a bunch of gets. Eventually, those are all going to fire off. We're going to hit the end of those callbacks, and then we would run the condition variable's callback. This performs just as well as the non-blocking one. If you use EV, it can sometimes perform better because libev has some really low-level optimizations for disk and network kinds of things. So EV can give you some pretty cool stuff. This is nice. We avoid continuation passing style. We don't have that pyramid of death going on there. It's very linear. It's fairly clean. If you're familiar with convars and how they work, you could look at this and see, oh, I see what's going on here. Some things are out of order. You're declaring your callback at the top of the program. That's going to happen last, but we declare it first. So it's a little bit funny that way, but it really, any event is nice. It gives you some really powerful primitives you could build really cool stuff with. It has decent flow. It's very flexible, and it's framework agnostic. You can see I just pulled that into Modulicious, and it worked fine. And because Modulicious is fairly agnostic as well. Very flexible, very powerful and fast. Flow, again, it's a little bit iffy there. Okay, we're going to look at promises for a minute now. I'm not going to spend as much time on promises as I did with any event. The promises module is nice if you're familiar with JavaScript background. Promises is this is the Perl implementation of the promise A specification with a couple of asterisks in there. But by and large, this is exactly how it was spec'd out. The first thing we do here, and in the Perl version, you really have to do something like this. You have to wrap. You have to have a helper or a function or something like that that wraps your deferred object, which is what implements the promise. Otherwise, you've got lots of boilerplate code. In this way, we kind of crunch up all the boilerplate into one spot. It performs just as well as EV. Here's our controller here, where we're going to handle a get on the weather URL. This is a promises function. It's called collect. You can see I declared it up at the very top there. And it makes three, so we're invoking get URL, which is the helper we just declared up there. So we just pass it a URL, very nice. It creates a promise around that URL and does a get for us. So that's very concise and nice. But you can, if we tried to do this in line, you could see we'd have tons of boilerplate in there at the same time. So once those three URLs, so these are happening concurrently, boom, just like the any event one. They're not waiting one for the other. They all go out, and then they all come back when they come back. And once they've all come back, then, right, that's the then keyword there that's also part of the promises module. Then we run our subroutine. And there's also, promises also has some very nice flow control and error handling. It's fairly mature. But it does require a little bit of boilerplate, but not too bad. Why would you use promises? It does give you some nice abstractions. Uses the promises pattern if you like that. It's also framework agnostic. You saw I just pulled that into Modulicious, and it works fine. There's a lot of nice things about promises. I don't have really much negative to say other than the promises pattern itself can be a little bit hard to grok. Okay, and now the moment you've all been waiting for is here. We're going to talk about Mojo IOLoop delay. This Mojo IOLoop delay combines the flexibility of any event's convars with some of the nicer abstractions and ease of use that promises has. So remember, our original problem that we're trying to solve is we're trying to avoid the callback hell, continuation passing style, and we want some good flow control over our program. So Mojo IOLoop delay has the same kinds of things that the other ones we've seen. It has some nice flat call chains, powerful primitives like any event, some clean abstractions like promises does, and you can mix and match your sequential or concurrent patterns. So if you want to do one thing after the other, we can do that. If you want to, if you have a URL that depends on a previous URL, you can wait, or you can, fire off 600 requests at the same time if they don't depend on each other. Very nice. So here is what a basic delay object use looks like. We create a delay object, and we run its steps method. In the first step, a step is a subroutine. The first step we're going to make our non-blocking call. And in the second step, we're going to receive our non-blocking results. It doesn't have to work like this. The non-blocking call still has a callback, which you could leverage and do some additional handling in there. But this is a pretty clean pattern, one that we've used fairly extensively. So steps are just subroutines that you define. Each step receives a delay object as its first argument, and also all of the arguments passed to it from the previous step. So the steps can actually talk to each other. It's very nice. The next step will not run until these two conditions have been satisfied. You have to create what I call a step callback using begin, and then that step callback has to run, has to fire off. So here is our callback. If you'll notice there, that first user agent get has a callback, and it receives a user agent, copy of the user agent object, and a transaction object. So we're going to make use of that here. This is what we would. This is what we would do in steps. We make a step callback. This is how you do that. You call begin. Now we assign that. We're assigning that to a variable. Once you've made your step callback, you pass it to the. It needs to be invoked. Now it shouldn't be invoked until the thing you're waiting for finishes, and so we put it into the callback of the non-blocking URL request there. The step callback arguments here get passed to the next step. So we get the @ underscore contains user agent transaction because that's what get passes to its callback. So we are that callback now, and so we get all that stuff. So there are some comparisons we could make to any event. Any event condition variables have a begin and an end that we saw. We fired off the begin, and when we're done, we fire off the end. And that tells the condition variable we're done when it gets down to 0. Mojo IOLoop delay only have begin methods, but that begin method is very powerful. It returns what we would normally call the end. It's a callback. It returns a callback. So it's a function that returns a function. So it might look something like this. If we were to implement it with any event convars, we would have our condition variable, we would increment the counter, and then we would return a subroutine that, when called, would invoke the end, decrement the counter again. This isn't really how it's implemented, but this is, if we're talking in any event terms, it works kind of like that. Okay, so here we are again. I'm gonna show this a few times in a few different ways. There's some subtle little things here. Again, we create the step callback at the beginning of our first step. We invoke the step callback inside of the non-blocking callback. The one argument where we here the begin method takes an argument, and that is a number, and that number tells begin how many arguments to shift off at the end. Now, why would that be important? We'll find out in just a moment here. So we run our callback, and what happens is that instead of getting both the user agent and the transaction, we only get the transaction because we've shifted off the first one. It turns out that the Modulicious non-blocking calls, nearly all of them, that first argument doesn't have any real use. And so the common case is that we would shift it off anyway in our step or something like that. So this makes the common case very simple. In fact, the default to begin is 1. It's to shift off the first argument. So we're going to look at that. Here it is right here. This one and the one before it are exactly the same. There's a little implicit 1 there. So we're shifting off that first argument. We're invoking the step callback, and then we move along. So if all you're doing in your non-blocking callback is invoking the step callback, you can save yourself some time and some boilerplate. And this is a very common pattern here. You can see that instead of making the step callback outside and then passing that callback in, we just make the step callback right as the non-blocking callback. Very powerful. Makes it very concise, and we also then just get the transaction object in the next step. This is, again, a fairly common pattern, and makes it very, very clean and tidy to work with. Okay, so we're going to talk about getting from one step to the other. We've seen some examples of this. Steps that make asynchronous calls must create a step callback before the asynchronous call. And then then it needs to invoke that when the non-blocking call completes. So these two examples on the left and on the right are functionally identical. The one you might use the one on the top left if maybe you needed to munge those arguments before you pass them on to the next step, or something like that. The one on the right is, you can see that we create our step callback, and we just pass that callback right in. But if you're going to be doing that, you might as well be doing that right there, where just create it right there as the callback. Again, this begin returns a function that will be called when the GET request comes back. Any questions so far? So steps that don't make asynchronous calls, you can just use pass. That's where maybe you've got a step that received a bunch of stuff from some previous steps. It's not making any non-blocking calls. You got to figure out a way to keep going on to the next step. Pass is what you would use. You could pass any arguments you want. You could add stuff, or add things to the stuff array, whatever. This is functionally identical to this. This, if you're not familiar with functional programming, this is a bit mind-blowing here. What we have here is we create a step callback, and then we immediately invoke it and pass it the stuff variable, the stuff array. It's, again, if you're not accustomed to functional programming, it's very uncomfortable and unfamiliar, but it's a cool pattern. And anyway, okay, so we're going to have a quick quiz because you've been so good. I'm going to reward you like to pretend you're back in school. So my question is, will the second step ever be called? And if so, what will it receive? Any ideas? Anyone not Glenn? Don't be afraid. Don't be shy. Is it going to hit the next step, first of all? It will.
I'm going to say yes.
Yeah, it will. It'll get called. What's that?
Yeah, I mean, you're using that common pattern where you're just saying
Yeah.
it's getting the callback
Yeah.
pass through.
So what will it receive? What?
It's going to shift the user agent off so it'll receive the transaction.
That's right. That's exactly right. Yep. So that's what we get. We get the transaction object there. Okay. Will the second step ever be called? And if so, what will it receive? Is it going to get called? All right.
Well, it's getting the subroutine references actually. You didn't say to execute. If you need an ampersand there to run inside the sub.
Yeah, you're right. It will not reach the second step here, because what we've done is we've declared a subroutine, but that subroutine doesn't run.
We need to tell it to.
Exactly. Now, so what happens here? This is a little bit tricky, because remember that step callbacks have to be created before you make your non-blocking call. If you don't, what's going to happen here is it's going to make the non-blocking call. It sees that there are no outstanding step callbacks, and so it just moves along, and there's nothing to move along to. So it's a dead end of code. And maybe the response comes back, but it has nothing to attach to. Everything's already been thrown on the floor, and this just stops right here at that step. So it's something to watch out for. Make sure if you're using the pattern where you need to manipulate the stuff before you pass it on to the next step, that you declare your step callback outside of the non-blocking. Okay, very good. How about this one? Will the second step ever be called? And what will it receive if it is called?
Receive the user agent.
Why is that?
Because you're not shifting anything off.
That's right. We've made our declaration there of begin 0, and this tells the step callback, don't shift anything off, just pass it all through. And then once our user agent's callback is fired, it will then pass everything it gets, which is the user agent and the transaction, down to the next step. Very good. There it is. It gets both of those. All right, 4.4. Will the second step ever be called? And if so, what will it receive?
Just the transaction that will be called.
That's right. It will be called. Yep. Very good. And because I can't count, What about this one? Will the second step ever be called? It probably will. If there's a case where the get user agent doesn't give you any arguments, it wouldn't. It's just a kind of a yucky pattern. I just don't do stuff like this. This is just a bad idea. Make sure that everything's clear. If you need logic, do it elsewhere. Or make sure that if you do that kind of thing, you have an else that also fires the step callback and passes it some different arguments, for example, and then handle that in the next step. All right, we get extra credit because you guys are so good. So will the second step call run, and what will it get? Yeah, it'll get 1, 2, and 3. That's correct. Yeah, it just goes. Yep. What about this? This is a little bit different.
You said it only took one parameter, so does it just shift off the first one, or does it?
Yeah, it'll just look at the first one. So what happens here? This is a trick question. What we're doing is we're declaring a step callback, but we're never calling it. That's all we're doing. Well, all we've done is declared a step callback, and everything just stops right here. So it's what we really want. Pay attention to the slide transition here. It's gonna look almost the same. Ooh, see? We create our step callback, and then we immediately call it. Yeah. So what will the second step receive here?
2, 3.
Why is that?
One gets shifted off.
Where's the 1? That first argument?
Yeah, the first argument.
No, that's not right.
No.
You are right that it will receive 2 and 3, but 1 is the implicit argument to this function. Like that. See? That's where the argument for the step callback goes right there. So this will receive 1, 2, and 3. The previous you were right, but not for the right reason. Yeah, good. Okay, so that's steps. So we're going to finish up here. What we've got is here is concurrency. This is how to do some. You can make multiple callback steps at the same time. The next step will not run until all of them have come back. You can see how succinct that is. That's a nice tidy pattern. It may be it's a little bit larger than the promises, but with promises we made a helper to make it clean. You could make a helper out of this and make it really tiny if you wanted to. So there's our first step. We make 3 concurrent calls. It goes boom, 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 fires 3 network calls off. Eventually, those might come back. And when they do, we'll be down into the next step here.
There's some other non-blocking things inside of this second step, and those ones would have to wait for the first group to complete.
That's correct. Yeah, this second step will not run until we get all of our responses back. Mm-hmm. And the other nice thing, pay attention to this. This is kind of cool. In the render call there, you'll notice that I do moon shift, slow shift, IP shift. This is, again, kind of a functional pattern. Those shifts implicitly shift off at underscore. We took the delay object out first, leaving our at underscore with the 3 things that we passed in from the first step. It preserves the order, which is really nice. So we know that the first thing that's going to come back to us in the second step was the first call we made. It's going to be that first one. Even if it didn't happen in that order, we get them in the order that we called them. So that's very nice. So that's concurrency. Here's serialization. If we wanted to, here's our first step. We go get our IP. Now we need the IP address for our second step, so we have to put it into another step. Those couldn't run concurrently. Once we have our phase of moon, we're going to make a slow call. That could have been in parallel technically, I guess, but yeah. So and then once we get our result, we're able to do our render here. Okay, so now we're going to tackle our real microservice example. To refresh your memory, we're going to get our source IP. Once we have our IP, we're going to get our geolocation. Then once with that, we're able to get the other real information that we wanted. This is what it looks like. You can see that we're pulling out all the stops, and we're making a mixture of sequential and dependent calls and concurrent independent calls. Here's our first. We go get our IP. We go get our geolocation. With that, then we can make 3 concurrent calls and get our phase of moon, our air quality index and the actual weather forecast for our location, and then we render it. Now, this isn't bad, and I feel it's a pretty clear, it doesn't have a lot of boilerplate. It's very clear what's happening here. But what bothers me is that we have to pass data from one step to another. If I wanted to pass the IP address all the way to the bottom, I'd be probably doing stunts like we did with any event, where we declared this variable outside of the delay object, and we stuff some things in there, and then we reference it again later. That's not horrible, but I think there is a better way, and we haven't talked about it yet. So we're going to take a minute and talk about delay has a data method, and it's kind of like a stash. If you're familiar with Modulicious stash, or like a scratch space, it stays with the delay object. It's there for the lifetime of the delay object. It gets cleaned up when the delay goes out of scope. It solves the any event problem of external data structures floating around, and it solves the step problem of having to pass stuff from one step to the other. So let's add some of this data stuff. Here we are right here. This is exactly the same code we had before. I've removed the top and the bottom again for space reasons. So we invoke the data. It just takes like a hash. You have a key and a value, and that's how you assign into the data. We have the latitude, longitude we're stuffing in there. We have the moon, the AQI, and the temperature we're stuffing in there. This is actually worse because it makes it bigger. We do get one nice bonus, and that is that when you invoke the data method by itself, it returns a hash reference of all the things that are in it. And so if we put in it all of our response, then we can do a cute little thing like that and just JSON stringify all the things that we've put into that. So that's cool, but there's actually more things that we can do with data that makes this a little bit more powerful. We can abstract steps, for example. We've made a little helper here. I apologize for the brevity. There is a lot going on here with all this shifting and things. But the heart of it is that it returns two steps. This is a helper that will give us two subroutine references, two steps that link together. The first step makes our user agent request out to the URL and invokes the delay begin object, makes a step callback for us. And the next step, we get the results, because it's happened, right? This is the step that fires after the step callback fires. And then we assign it into the data hash. And then you can see at the very end, it's kind of cute that the data hash, or the data method returns the delay object, so we can just chain method calls, and we're going to invoke pass here, right at the end. So now we have cute little steps. We can call rec step, rec steps, and assign those things into the data, and then so that's short. That's kind of nice. But there's something else we can do here that's even better. I was wondering, can you call a delay from within a step? It turns out that Mojo IOLoop is a singleton object, which means that any time you reference it from any delay object or any step, it's the same one. There's only one event loop running. So that means all events get stuffed into the same place, even though they're coming from different steps and different delays and things like that. So wouldn't it be nice if we had a controller that looked like this, where we have a delay object, and we had some kind of a magic function that gave us the geolocation, and another one that gave us the weather, and then we got to render. So what would geolocation look like? It would look exactly like this. I mean, here's one way, right? We make a helper called get.geolocation. Now remember, this thing has to return a step. So what we're going to do is we're returning a subroutine reference here. That's the last argument, or that's the last call in this helper. But there's a lot packed in there. But this is what it's going to return. It's returning this subroutine reference. This is a step. It's a giant step. In this step, we create, we shift off our delay, and we invoke. Sorry, I'm going to point this out. We're making our step callback. This is the outer step callback, okay? Now we're making a new delay object here. Its first step is to go get our IP. Then it does all the things that we're familiar with. And then the last thing it does is it puts the latitude, longitude back in its own data space, And before it finishes, we assign that to the outer delay, right? The one that the outer step is going to receive. And we also, just for fun, we're going to pass it along in the bucket brigade of that data too, so that any steps that come after us can receive the data that we're passing along if they'd like that. Okay, so that's the geolocation step. Here's the weather step. I've shrunk it again because of space limitations here. I won't spend much time on this one, but you can see that it expects to receive latitude and longitude. So we could actually implement function signatures, use some function signatures with these helpers, and make sure that they're getting what they're supposed to get. That's new in Perl 520. Very cool stuff. With that, we can make our 3 calls, boom, 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 all at the same time. We receive those results here, 3 transaction objects. We stuff those into our local data object, and then we, again, pass those to the outer delay object, and we move on. So here's the best chef of all. This actually works. You have your controller here. You do a get geolocation. It does 2 things. It assigns what it gets into the outer data stash, and it also passes its stuff down the bucket brigade of the steps to the next one. Weather expects to receive latitude and longitude from whatever calls it. Well, the previous step called it, and unfortunately that's the one that had latitude and longitude. The weather then collects, its AQI, phase of moon, and things, and passes it down the bucket brigade, and that's why we're able to shift off at the very end here. We could also have easily done JSON $data, and we would have also, or $D data, and it would have been the same. Actually, it would have been all of the information. We would have had our IP address in there. We would have had, all the things that we've looked up and stuffed into that data stash. Very powerful pattern. So that's it. Now,
remembering what's on the stack.
Well, so ideally, you would treat these as like functions, and you would put them in a library. Yeah. And every function has what it's expected to receive and what it's expected to return. Mm-hmm. So if they were well documented, yeah, there is some black box going on there for sure. Anyway, there's still a lot of boilerplate going on, but that could, this is something Glenn could probably solve, right, with a plugin or something like that, where it's a step maker, right, or a delay maker. You could do some really fancy stuff with that. So that's Mojo IOLoop delay. It's the awesome. Any other questions? All right. Well, that's it for me.